Greetings and welcome. We've been talking about applying trigonometric functions. That's right, applying it, which means we're probably applying it to triangles of some sort. And our homework was starting on page 302. So here's question 13. It says solve each problem round to the nearest tenth. So that's why they rounded to the nearest tenth there. It says if angle A is 29 degrees. So here's angle A. All right, 29 degrees. And little a is 4.6, so there's my 4.6. It says find C, so this is what I'm looking for. All right, and let's see what we got. So from angle A's perspective, what is 4.6? The opposite leg, right? And what is C? Hypotenuse, because it's opposite of the right angle. So what trig ratio compares opposite and hypotenuse to some degree? Sine. So I'm going to say that sine of my 29 degree angle is equal to the opposite, so that's 4.6, divided by the hypotenuse, which is my unknown length C. All right. So if I want to solve that, there's a couple ways you could do this first move. You could immediately reciprocate both sides. Usually I'll just have students multiply both sides by c to get rid of the variable in the denominator, and then we'd have c times sine 29 is equal to 4.6. And then to get c by itself, sine of 29, I just want to point out, is just some number, okay? So it's being multiplied by c, so the way to move it is you divide both sides by sine 29. If I had to estimate the value of sine of 29 degrees, I'd imagine it's somewhere around 1/2, probably a little bit less than 1/2, because sine of 30 we know is 1/2. So dividing by 1/2, that's probably going to about double this. All right, so doubling that would be 9.2. So 9.5 seems to make sense. So if I was stuck on some desert island and had to try to figure this out without a calculator or a table, that's how I would have done it. So let's see. Oh, I could reference my calculator here. So I'm going to do, here we are, 4.6 divided by sine of 29, of course ensuring that I'm in degree mode, which I am. And I hit enter, and I get 9.488, and they said to round to the nearest tenth, so I'd call that 9.45. Huh. Oh, wait a minute. Sorry, 9.5, yeah. Yeah, what am I saying? What am I saying, guys? 9.5. Thank you kindly. So that's the general idea, where we technically have a whole bunch of formulas you could think about it as, right from SOHCAHTOA. And all I'm going to do is plug in what I know and solve for what I don't know. So I know that sine of an angle, right, theta, that's a sad-looking angle, is equal to the opposite leg over the hypotenuse, and that ratio is true all the time. So basically, by knowing this formula, I just plugged in all of the components I had, and then I solved for the one I didn't have, which was the hypotenuse, and I'm golden. All right, so that's the general approach to these kinds of problems. Let's look at 25. It says, the longest truck-mounted ladder used by the Dallas Fire Department is 108 feet long and consists of 4 hydraulic sections. Gerald Travis, aerial expert for the department. Wow, that sounds amazing. Can I be the aerial expert for our school? I think I want to be. I'm self-declared. Let's see. Indicates that the optimum operating angle of the ladder is 60 degrees. Oh, this is getting interesting. The firefighters find they need to reach a roof of an 84-foot building. Assume the ladder is mounted 8 feet above the ground. Oh man, this is crazy sauce. So let's see. Let's draw my little fire truck. And I've got like the ladder, right? And it's at a 60-degree angle. Oh, it's already going crazy there. So here's my ladder. 4 hydraulic parts. Here's the wheels on the truck. And then they're like all like, boing, right? Wicked cool fire truck. And there's a building, I imagine. And here's the building. And I also know that, let's see, I know some dimensions. I know that this length is 8 feet, right? I know that the ladder can reach what was it, 108 feet. I don't know if it's fully extended yet for this problem. I'm just labeling it. I know that this is a 60-degree angle, right? I know that this building's total height is 84 feet. Man, it was lagging out at the end there. So 84 feet. And let's see. Yeah, okay. So I think I've done this well. Right, so here's, last thing I really need is, I need some cool fire effects. Special effects. There we go. Now it's believable. Now there's a sense of urgency to this problem, like, oh man, we better solve this fast. Let's see. Question B, how far from the building, oh wow, this is interesting, should the base of the ladder be placed to achieve the optimum operating angle? Well, so I think, let's figure this out. I might simplify my diagram for part B into just a right triangle. Whoa, oh, I just lagged out on my battery. Por qué? Let's see. Quick repair, plug in a cable, solving the problems of the world. My battery died on my wireless tablet, but it's okay. Problem solved, because I'm an aerial expert. And, there we are. I'm back! Haha. All right, so let's re-summarize this in just to a simplified triangle. So let's see. So I know that the optimal angle is 60 degrees. All right, so that's definitely what I want. I'm looking for this horizontal distance. I know this is still going to be 90 degrees. What is the height from the top of the truck to the top of the building? Well, yeah, it's 84 minus 8. That's kind of like a segment addition postulate. The big length minus the little length will equal the leftover length. So 84 minus 8, so that's what, 76 sounds right to me. So here's the problem that I'm solving in B. I'm specifically interested in how far from the building should the base of the ladder be, right? Right, this is the dimension we're interested in, right to there. So let's solve this, or let's write an equation. So for this, from this angle's perspective, 76 is which leg? Opposite. X is which side? The adjacent leg, right? So the trig ratio that compares those things is tangent. So tan of 60 degrees is equal to 76 over x. So to solve this, first move, I'm going to get x out of my denominator. You didn't have to use the variable x if you didn't want. I used x, not only because it's a typical variable that people solve for, but also because I was thinking about this is a horizontal distance. Ooh, and x is usually a very good horizontal representation of a variable. So let's see, divide both sides by tan 60, because tan 60, it's just a number, all right? And in fact, we might even know what tan 60 is. I might not even need my calculator on this. Does anyone remember what tan 60 is? Let's see, hand trick it. 1/2? No, it's, yeah. Let's see. Put down the 60-degree finger. It's the square root of the fingers to the left is 3, divided by the square root of the fingers to the right is 1. So square root of 3 over the square root of 1 is just square root of 3. All right? I think they're probably going to be content with an approximation, which typically is what you're going to get with this, which isn't that bad. So 76 divided by the square root of 3, I got 43.88. Right? So 43.88. Yeah, that's right. They rounded to the 10th. Okay, man, this building's still on fire, though. All we've been doing is math. People are dying, people. Let's see, question C. How far should the ladder extend to reach the roof? All right, so even though the ladder's potential is 108, it's hydraulic powered. It's got 4 sections. Actually, I might even be able to determine what the minimum length of the ladder is if I know it's in 4 sections. I imagine there has to be some overlap between the ladder, right? So I wouldn't just divide 108 by 4. it'd probably be less, each section is probably a little bit greater than 1/4 of 108, which would be what, 27? So each section of the ladder is probably at least 27. But anyways, people are still dying here. So now I'm looking for the hypotenuse, right, for part C. So I mean, if you want to redraw your triangle, you can. So this is 60. This is 76. This is 43.88 now. And I'm looking for the hypotenuse. I'll just call it H maybe, or L for ladder length. I don't know. Doesn't matter. I would actually choose to ignore the 43.88 now. I know that we could actually use this and Pythagorean theorem to find the missing side. But let's use our new skills, and let's use the information that was given to us to find this new side length. All right? So 76 is still the opposite. H is the hypotenuse. Here's my angle. What trig ratio compares those two things? So I'm going to say sine of 60 degrees, which you guys should already be thinking about the hand trick in your head, right? 76 over H. So to solve, I would do the same classic step, multiply by H. You might be familiar with this step by now. Actually, it seems like so far all of the examples that I've done from the homework have been dividing by our trig ratio rather than multiplying by our side length. It's not always the case, so don't be thinking that. And sine of 60, hand trick, what is it? Square root of 3 divided by 2, right? So that's the same as 76 divided by the square root of 3 over 2, which is the same as 70, if I multiply by the reciprocal of this fraction, 76 times 2, what's that, 140 plus 12, 152 divided by the square root of 3 would be kind of an exact value. I could also then, get rid of the square root of 3 in the denominator. But we're just going to go for an estimate. So I'm going to do what am I doing? 152 divided by the square root of 3. I got 87.76 as my answer, and I believe theirs was similar to that, 87.8. So let's go rescue those people. This is going to be good. It's going to be good. All right, so that's the general idea. You draw a triangle, you solve it. And so far, these have all been right triangles. And today, we're actually going to end up learning the last technique of solving right triangles. Let's see. Let's look at one last problem. Let's see if I can at least get it set up. All right. Let's see. Problem 26. When a 757 passenger jet begins its descent to the Ronald Reagan International Airport in Washington, D.C., it is 3,900 feet from the ground. All right. Its angle of descent is 6 degrees. Right there. All right. What is the plane's ground distance to the airport? Okay, so ground distance, they're specifically talking about this horizontal distance. All right. They labeled that nicely for us. So the first thing I'd realize is 6 degrees is not the angle I'm looking for. Obi-Wan Kenobi. What is the angle I'm looking for? Yeah, it looks like these two angles would be complementary. They'd make a right angle, so 90 minus 6 is going to be 84 degrees. I agree. So from this angle's perspective, the ground distance is the opposite. The height that I know, I usually say elevation of the plane, but it's altitude, right? In my mind, it's kind of the same thing, but elevation, I imagine, is more specifically referring to a mountain's height or your location above sea level, not while you're in the air, but while standing on the ground. What's this dimension as far as our angle's perspective is? Well, what side is this? That's the adjacent, and then yeah, so that's going to suggest tangent's going to be helpful for us. So I would set this up as saying tan of the 84 degree angle is equal to the opposite, which is my unknown. I'll just call that G for ground distance maybe, over 3,900. And I was going to skip the work on this, but this one's the first problem that we're actually just solving by multiplying both sides by 3,900. So G is just going to equal 3,900 times tan 84. Let's see, can you hand trick that? No, I don't have an 84-degree finger. So 3,900 times tan 84 is, I got 37106.02. And that seems rightish to me. And then let's just talk about the last thing. How far must the plane reach to the runway? So they're talking about the actual distance, right, from the plane's nose, which is the hypotenuse in our case. So, right, the distance traveled, they're saying. So to figure that out, what trig ratio should I use? Well, I'll compare the side I know or was given to the side I don't know. So that's adjacent and hypotenuse, so I would use cosine for that. So I would say cosine of 84 degrees is equal to the 3,900, the adjacent, divided by the hypotenuse. All right, opposite, right, yeah, adjacent over hypotenuse, yeah. So, and then solve this. H is going to end up equaling 3,900 over cosine 84 for that when we do some work. So H is going to be approximately, let's see, divided by cosine 84, 37310.41. Now, this being the hypotenuse, I would expect it to be longer than all of the other dimensions. Yeah, it's longer than that, and it's longer than that. Yeah, not by much in this case. Well, I guess this was a really big angle, you know. Like this triangle is definitely not to scale. Like it'd probably be much more of like a sliver comparatively, right? So anyways, there we go, friends. Thanks for watching. Have a great day. Bye-bye.